All right. So today I'm going to go through the last thing that I haven't done in Chapter 7, which is Rayleigh Benard convection. And I don't do it because it's kind of the least satisfying section in this chapter, because it doesn't get you a nice, clean, here is where the thing blows up, or whatever. You get a class of solutions at the end. We'll talk a little bit about this. And then we can talk about other stuff that you guys feel like talking about, because this actually is the last thing that I haven't spent class time on, and I don't want to start anything new like turbulence, which is really what I want to talk about. I'm not going to start talking about turbulence today because we've got a midterm and a homework set and other stuff in the way. So, okay, so the last thing, Rayleigh Benard convection. So this is pretty simple physics. As far as, oh, I got a red one. In color. So here I got a pot with water. There's water. Pretty technicolor, guys. And we're heating it from the bottom, and we want to know what happens. So the first thing I'm going to do is I'm going to set up the equations and do the math. And the second thing we do is we get a differential equation that then is a giant headache to solve. And it becomes a project by itself, and you stop losing the physical significance. So we'll get to a differential equation that then I make you go read a bigger book. But the physics setup is pretty interesting. And stuff that should be basically straightforward, in big air quotes for everybody. So the first thing that we start with is we start off with the temperature equation. I just wrote it there. Should I derive that for you? Is that how I want to start it? Sorry, let me commune with the book. Let's see if I like the way he did it better. Usually not. Yeah, fart. Anyway, he doesn't derive this equation, but I will. So, okay, he starts with d by dt plus v dot grad t equals kappa del squared t. So, what kind of an equation is this? So it's got a name. What's the left-hand side?
It's like burgers.
It's like burgers. It's like, that's right. And what else is it like?
Heat equation.
What's that?
Heat.
Yeah, so it's like the heat equation. So this is advection. This is like Burger's equation. Burger's equation is just advection. Navier-Stokes has an advection term, and you can see this is d by dt of a thing plus v dot grad of that thing. So this is just the full derivative again. But because of the v part, it is advection. It's more than just the full derivative. It is the thing getting pushed around by the velocity of the flow. And this part, that's what I wanted to do today. I wanted to talk about diffusion, but I don't have those notes. But anyway, it was too chaotic a morning for me to get my head straight, and now I realize what my head was supposed to do. Anyway, or can I? Can I do that? No, I'm not going to try to do that. So this part is diffusion. So this is an advection diffusion equation. That means it pushes stuff around by the flow, but also the stuff seeps around by itself. So, and the grad squared is the important part for the diffusion. So del squared of something is means just kind of wandering around. So this is like if I have, sorry, there's only half a lecture in my head for what I want to say about diffusion. So where does this come from? So we had an equation. Sorry, I gotta cheat and make sure I don't write it down wrong. Because if I write it down wrong, then I do everything wrong. Hold still right there. Okay, so okay. Let's go back to the beginning. Why am I going back to the beginning? Well, for two reasons. One, to make sure that I do it right, because this is the kind of thing that I screw up if I don't do it carefully. But two, also, I just want to iron over these ideas again with you guys. dq is dE plus P dV. And I just wanted to like put this up again. So whose law is this? This is the first law of thermodynamics. If you haven't taken thermo, no shame if you didn't know that one. But this is the first law of thermodynamics. It says that heat flow is equal to the change in internal energy plus the work done. So this is like Maxwell's equations or F equals ma or Schrodinger's equations in terms of importance of equations that you should know. And we say, okay, we make this all per unit mass. Whoops, that's got to be a 1 over rho. And then we do a little bit of calculus, and we're left with rho dE dt. Oh, that's a partial. No, I was right the first time. dE dt plus v dot grad p equals grad k grad t. And there's a minus sign there. I'm sorry, this isn't right. I wrote that backwards. P div v. There you go, that's better.
What's the E in, yeah, what's that?
This is internal energy.
Okay.
That's this E. It's internal energy per unit mass. Now, I know that dE is just CV dt. So energy is just proportional, internal energy is just proportional to temperature. So if we drop this in here and use a little bit more thermodynamics, the other part is this side here. So I've got this grad K grad T, and this is how we derived it in the first place. If K is the conductivity, so this is how much heat flows through a surface area per unit time, per unit length. If this is a constant, then it comes out, and this just turns into K del squared T. So this just turns into diffusion. And this on the right-hand side, the E turns into a T, and we do a little bit of algebra with the P to turn it into a temperature again, and then we're left with this advection diffusion equation. So this is not a complete proof or a rigorous proof. I'm just kind of pointing out the landmarks of how we get there. So we start with the first law. We expand that, and then we're left with this advection diffusion equation for temperature. So the left-hand side is pushing stuff around, and the right-hand side is smearing stuff out. Does that make sense in the most technical of terms? So what do we do with this? So if we assume that I'm heating it at the bottom, and there's another temperature at the top, the most reasonable assumption is that the temperature gradient is going to be basically linear from the top to the bottom, right? So we have some bottom state, which we'll call B, and some top state, which we'll call little t, upper. There's no good letters for that because T is time, and big T is temperature, and mu is velocity. Yeah, we'll just call this one the bottom. Because I only need to refer to the bottom. So the first thing to do is, okay, so what we're going to do is we're going to say, one, it's in steady state. Okay. That's kind of a dumb idea because I'm dumping energy into the system, so it being in steady state, you've boiled water in your stove before, right? That's not a steady state equation system. It boils. So you set the temperature up so that it is a steady state. So that means to first approximation. Oh, I'm sorry. Let's back up for a second. The equilibrium solution is in steady state. The whole thing is going to boil. The equilibrium solution is in steady state. I knew what I needed to do, and then I started talking about the wrong reasons. So back up and just erase that bit. So okay, the background solution is in steady state. And we're going to perturb that. So the background solution is in steady state. So we're left with kappa times del squared T equals 0 because it's in steady state. So that means that if I integrate this once, I get a constant. And if I integrate it again, I get a line. That means that T, and how are we writing it? T equals T bottom minus beta Z. And beta, I didn't write it down, is T top minus T bottom over D, where D is the depth of my fluid. It's just the gradient in temperature. You okay so far? You look a little confused?
Yeah, I'm good.
Okay. So we say steady state. We've got this advection diffusion equation. Because we're in steady state, the diffusion means that the thing's just going to be linear because of the diffusion process. Okay, so that's what the background temperature is going to be. Let's talk about what the density is going to be. So the density has some thermal expansion. And so we deal with a thermal expansion by saying that d rho is going to be minus alpha rho dt. Now I could make this d rho dx or d rho d time. Both are fine. I'm just going to leave it as a little d rho. D rho is minus alpha rho t, where alpha is defined by this equation that I just wrote down. So I'm saying that this is what alpha does. So let's talk about that for a second. D rho dt, let's call it be explicit, equals minus alpha rho dt dt. So this means that the temperature change is linearly proportional to the density change. Back that up. The density change is linearly proportional to the temperature change. So there's a fractional change. This is how most things expand and contract. So if you heat something, there's some proportionality constant that determines how much your density goes up or down depending on how much you heat the fluid. And it's negative. Why is it negative? If something gets hotter, what's the density usually do?
Decrease.
Usually goes down, so the negative just makes sure that we have that in line. So, okay, so we're still talking about the equilibrium solution for this boiling water pot. What's the density going to do as a function of z? Density as a function of z is going to be rho at the bottom plus d rho dz times z. Okay, so we've linearized it, but that's okay. It's a good bet that it's going to be linear in the first place because temperature has to be linear. So this is what density does. So we expand out what, sorry, I have this data here that I missed. Oh, sorry. My handwriting is sometimes awful, and it looks like a minus sign, but it's an equals. So I'm like, where the hell does this other term come from? Anyway, so what is d rho dz? This is just going to be minus alpha rho dt dz. But we know what dt dz is. That's just beta. So this is minus alpha rho beta. Right? Okay, so let's see. I'm going to go over here and write down our equilibrium solution. On this board over here. I'll need it in a second. Let's see. Rho naught of z is the density at the bottom of the fluid plus z times minus alpha beta rho at the bottom. Let's simplify that. Oh, I'm sorry. There's another minus sign. Beta is negative 2, so we get a minus sign and a minus sign that cancels. 1 plus alpha beta z. Okay, so my background density solution is just going to be whatever it is at the bottom plus this linear decrease as we go up to higher densities. So now we perturb everyone. These notes are terrible. They don't make as much sense as the book does. So let us perturb Navier-Stokes. We're going to perturb Navier-Stokes in a funny way. We're going to use this equation, this approximation called the Boussinesq approximation, which means that density can change if gravity does it, but that's it. So we start off with rho dv dt plus b dot grad v, which I'm going to write down every time, even though I almost always throw this term out. But I write it down because it's going to be really important next Thursday when we start turbulence, because this is where all the fun comes from. So minus grad p plus rho g plus u del squared v. We have Navier-Stokes. Oh, I'm not looking at the top. And we'll expand this, and so we're going to expand it in a couple of ways. So this goes to rho naught plus rho 1. And rho naught is not just a constant anymore. Rho naught is this complicated thing. So we can't just throw it out because it's constant, but we can throw it out because it's hard to make things denser. So we'll come back to that in a second. dv1 dt, we'll assume that it's not moving initially. Plus this term just goes away because it's going to have a v1 and a v1. That's all that's going to be left. Equals minus grad p naught plus p1 plus, let's expand out this density is rho naught minus alpha p1 times g plus mu del squared v. Where did T1 come from? Okay, from the beta. So I cancel out the things that are higher order and the things that are in the background equation. I'm left with rho v times dv1 dt equals minus grad p1. That all looks familiar. Minus rho b alpha p1 g. G is the gravitational acceleration plus u del squared v. Which looks basically like Navier-Stokes, but now we have this extra term that is our gravity. Well, the gravity perturbation from the little wiggle in temperature. And then from here, we'll linearize this, and we're left with d by dt of t1 from that term. Equals beta v z1 from this term, because that grad t turns into just the beta. Remember, temperature is linear, so the derivative is just the coefficient that's in front of the line, and v is v. So we're left with just beta. This is just the temperature derivative times vz plus a diffusion kappa del squared t. Okay, is everybody on board? Basically, yeah.
So why does one row become rho naught plus rho 1 and the other becomes rho naught minus alpha t1?
So this is rho naught plus rho 1. So it's the same rho naught plus rho 1, but in this, I didn't write it all out because this rho 1 cancels out because it's second order. So I've got a density that's in front of the velocity, which is the density that used to be under the pressure gradient, but this is the density. So we're expanding all of them as rho naught plus rho 1. This one, the rho 1 touches the v1, so I don't bother, I'm not going to bother expanding that out with everything that it is. It is that up there, but I don't care about that. So I just didn't bother writing it out because I was going to scratch it out right away. Does that make sense? So now again, I've got two equations that we've linearized, and now we've got to, again, combine them and finally, let's see what we can do. Forgot I hate this one. Let's just use this one. So I take the derivative, so I take the, let's see. Right, so we take this, and we take the curl twice, and that gets rid of this gradient term. And did I leave better notes in this? Yeah. So I take the curl of this equation twice, and we're going to use the fact that del cross v is just minus del squared v. This comes from one of those vector identities that's kind of gnarly. So I take the curl of this equation twice, and this turns into just a del squared term. And this turns into also a del squared term. Where did that come from? My notes made so much sense a minute ago. And we're left with, there we go, d by dt of Vz del squared Vz equals minus no, the P goes away and we're left with alpha times G times del squared T. We're just taking the Z coordinate, so this is curl of T, so if you actually do that out, you're left with dt by dx squared plus d squared t by dy squared. This is the Z component of the second curl of the temperature plus mu del squared V. And again, so what was the other one? Oh, and the temperature one we already have. So the temperature one we have no, not T1. Plus mu del squared T, no, kappa del squared T. Okay, so then the stunt. All right, so the important physics that I wanted to talk about initially is that, so first we're linearizing temperature. Second, when we do this expansion, we throw out the small fluctuations that aren't caused by gravity. The small fluctuation, or the fluctuations that are caused by gravity, we hang on to. And we're going to curl these equations again, and we're going to make the same assumption but that we usually make, that V1Z is going to equal e to the ikx and stuff. So, but we're one of the complicating problems with doing this that's more complicated than when we have the free solution is now we have a boundary in Z. When you have a boundary in Z, you can't use the just plane wave e to the ikx solutions anymore. So we use just some unknown equation Wz. And then for the rest of the behavior, we can assume that it's going to go like e to the sigma t plus kxx plus ky. There's an I on these two, but not on time and not on W because of the boundary conditions. So I like just saying I e to the ikx minus omega t for everything, and when you have free space you can do that. When you have a boundary you can't quite do that. So we make an assumption that Vz is going to have this form, and then the temperature is going to have another form, theta of Z, times again e to the sigma t plus kxx plus ky times I. So we have something that's going to oscillate in x and y, but be probably exponential in time. And we don't know anything about the Z behavior, but it's going to be wave-like in x and y because there's basically you have free solutions in that in those directions. Let's see. So we combine these two equations and we're left with I'll just start up here. And then we're left with this gnarly third order equation, which goes like d by d z squared minus k squared equals it minus r k prime w. And we've non-dimensionalized this with this Rayleigh number r, which is alpha beta g d to the fourth over kappa times the viscosity. So what this equation tells us is how the z velocity, so remember W is the z velocity, how the z velocity is going to evolve in space. Because you notice there's no time on this anymore. We'll just assume that we're looking at marginal stability, because we know if we turn this up, it'll convect. So when we rearrange all our dimensional quantities, we can rearrange them into the Rayleigh number. So what this tells you is how likely is this object to start to convect. It's not as simple as with the two interface scenarios, because they're explosive, but you can work out regions of stability, and there's a cartoon in the text where they look at this, where this is wave number k, and this is the Rayleigh, and we have this unstable region and this stable region down here. So what you can find is that different wave modes are unstable in different spaces. So before we had nice a nice dispersion relationship that said something like k minus v under the square root, so that you could say simply something about the wave numbers that are going to be stable. Similarly, when we did gene stability, we had omega squared equals c squared k minus k genes squared. So this is nice and simple, because you can see that as soon as k genes is smaller, k is smaller than k genes, this is a negative number, right? So I got a squared thing that's a negative number. The Rayleigh Benard is a lot more complex, because it's a higher dimensional system. And really, at the end of the day, I have not a ton else that I want to say about Rayleigh Benard. Mostly Boussinesq is the important bit that I wanted to talk about. All right. Is there anything else I care about Rayleigh Benard? Not really. All right. So that's it for that. So we have a homework coming up. Does anybody have questions on the homework that they want to talk about? Otherwise, what's something that you guys would like to see me do better? Otherwise, I'll do the two-fluid interface, because several of you are missing that. Anything in particular? Well, I'm going to go through and set up this two interface thing again, primarily because I'm going to ask you to do it for the homework, and it's kind of complicated. So I'll just do that again, unless anybody has any objections. Pretty good. And I'll go slow. Where'd it go? Okay, so we start off with two states, rho and u, or rho prime and u prime. We start with Navier-Stokes again. So dv dt plus v dot grad v is 1 over rho grad p minus grad phi. So this is Euler. And what we're going to assume is incompressible. And 2, we don't need to assume. We can just look at the problem and say, because of the way it's set up, it's not rotational. Now, incompressible by itself is not enough to allow you to use the potential flow. It needs to be irrotational as well. So we need to have div V equals 0, and that's for incompressible flow. But not rotating says that curl of V is 0 as well. And when curl of V is 0, then I can write V is minus grad phi for some phi. And this shifts my problem from being a vector problem to being a scalar problem. And that's nice. I can get all the vector business that I need out of just taking derivatives of this scalar. So I rewrite this, and I use a vector identity to rewrite this one, and I didn't write down which vector identity that is. And this turns into d by dt of minus grad phi plus grad 1/2 v squared. And there's another vector identity when you have curl of, anyway, I'm not going to, my memory's not going to give that one to me for free. Equals minus grad p over rho. Notice I can pull this, I can pull rho into the derivative y.
Constant.
Because it's constant. Minus grad big phi. So I used one vector identity, but other than that, I just plugged in things. So now I have everything in the gradient, so that I can say grad of d by dt of my potential plus 1/2 v squared plus p over rho plus big phi is 0. Just pulling everything over. Now I'm left with good equation 1. I'll write on this board. d phi dt is a minus sign there. Plus 1 v squared plus p over rho plus capital phi equals 0. So this is still Euler's equation, or Navier-Stokes equation. We just wrote it like a potential, because I can. So now, fact 1. The potential is got to equal minus u x plus my perturbation. So my background potential is some big velocity v u and some big velocity u in the top and the bottom. So since this is constant and in the x direction, so this is x and this is z, since u is constant and in the x direction, then I know that phi is just equal to minus u times x up here, and phi prime is equal to prime prime minus u times x down here. So that's my background solution. So I'll perturb that like this. I also know, this is just another fact that I know, del squared phi equals 0. And this is going to be useful in a second. So this says that d squared phi dx squared plus d squared phi dz squared equals 0. That's what del squared phi equals 0. And we're not going to ignore the y coordinate for now. Yeah.
The parentheses, the grad, and all that. Is there a negative in front of the?
There's a negative there. All right. Useful fact. I'm going to write this useful fact over here too. Phi equals minus u x plus phi So the next thing we need to talk about is actually what the interface is. And this is kind of weird. Where is all this? I'll work here. So the interface, so this is z equals 0, and this we'll call xi. Xi is the height of the interface. And so what are the things that we know about xi? So at the interface, I know that the time derivative of xi is the velocity of the gas, of the fluid. It might be a gas. It might be not a gas. So that tells us that Vz at z equals 0, or z close to 0. The fact that it's 0 doesn't matter for us now. I'm just saying where it is. It's not this everywhere. Vz is equal to dc dt. So I can say two things about this. The first thing, I know I know what Vz is. I know how to get this from phi. So this is minus d phi dz. And this is a full derivative. So if we expand this out like a full derivative, then we're left with partial xi, partial t, plus v, but I know what v is. V is just u. Dot grad d, and grad is now in just one dimension, and this is vx, dxi dx. Is everybody happy with that? Does that make sense? This is, I think, one of the weirder parts of this derivation. We get here, and then after this point, it's a bunch of hairy algebra, but this point here is where the actual physics is. So holler if this doesn't make any sense or you want me to explain this better. So Vz is just the velocity by interface, but also that is equal to d phi dz, and also this is equal to dxi dt plus u dxi dx. And I have one of these for the primed coordinates and one for the unprimed coordinates. And xi, there's only one of those, so it's not primed there. That shouldn't be primed. So I have two equations actually here. I have that minus d phi prime dz equals dxi dt plus u dxi dx and u prime, and one without the primes. So let's leave this one without the primes and this one with. So now I have these two equations. Okay, let's write these over here. We'll be useful in a second. Minus d phi dz equals dxi dt plus u dxi dx. That is true at z equals 0. And then I'm too lazy to rewrite it. There's also a prime version. Okay, so now I'm going to drop in all of my Fourier analysis. I'm going to write these. I'm going to write these definitions over here. So C1 is our derivative. We're going to assume that this goes like e to the I kx minus omega t. Phi 1, I'm not sure why the book uses C and not B. It's a little annoying. I kx minus omega t minus kz z. And then phi prime is going to be c prime e to the I kx minus omega t minus kz z. Okay, so here I've just here what I'm doing is I'm invoking the entire machinery of Fourier analysis and linear algebra by changing basis. So this is a whole basis transformation, but I don't really need to think about it like that. I can just think about it as I'm just going to assume that this looks like this. The fact that it's a basis transformation we can sweep under the rug for right now. So now I have three waves. I have, and the important bits are now the coefficients in front of the waves and k and omega on the inside of the waves. So we need to find out the relationship between k and omega, and we're going to need the relationships of these cofactors in the first place. So I can plug all of these into this equation. And that turns into, so we've got minus d phi dz equals dx dt plus u dx dx. So this one turns into minus c times, I'm taking a time derivative, I omega, and there's a minus I omega, times, let me do that again and not screw it up. The time derivative brings down a minus I omega. Then I got a minus sign from the thing, and then I've got c e to the I k x minus omega t. And then on the right-hand side, I've got an I omega times a plus u minus I k u times a. Did I do that right? Let me rewrite that again without screwing up the minus signs. I times minus omega plus k u times a equals minus k times c. Oh, I did it wrong. I'm not firing on both cylinders today, because I had said something totally wrong. So whatever I had written down here that you had written down, you can just scratch out because it wasn't right, because I had an omega on front of the k. Okay, so d phi dz brings down an ik because it's the z derivative. And then d phi dx brings down a k, and then the dx dt brings down an omega. So I got an equation that looks like this, and then I'll have another equation that looks very similar. I times minus omega plus k u prime times a equals plus kc. Oh, that's something I forgot to say over here. One of these is a minus, and one of these is a plus. So when I look at, so I've got kx and I've got a kz. Oh, that's a kz. Is kx and kz the same? I gotta go check that. We gotta go look at kx and kz. But also, z on phi has got to go to 0. Oh, and it should be imaginary. Boy, I screwed this one up like four different ways. So phi is I kx minus omega t plus kz z, but this isn't an I. Why? Because there's a boundary there. That's not a free boundary. It has to go to 0 at infinity. I can't have my interface move the top of the atmosphere. I mean, an ocean wave breaking in Tahiti is not going to cause anything to happen at the top of the atmosphere. So this has got to fall down exponentially in both directions. And phi prime has got a -1. So this is a prime, this is not prime. Yeah. So I have these two equations. Okay, where did this come from? These two equations are the motion of the interface expressed as amplitudes of Fourier. Yeah.
Is the C prime as well?
No, that's a good question. It's only one C or A. No, I'm sorry. There's a C prime and there's only one A. There's a C and a C prime and only an A. Thank you. Because there's one A because the interface is shared by both top and bottom of the fluid, but then there's a C prime and a C in the top and the bottom. That makes sense? Okay, so let's write these over here because we'll need them in a second. I times minus omega plus k u prime a equals minus k c prime and I times minus omega plus k u a equals plus k c prime, not c, c not prime. Okay. Need one more equation because I have, how many equations do I have? Oh, I didn't talk about kz. So from this one, d phi dx squared plus d phi dz squared equals 0. I have phi equals e to the ikx minus z minus kzz. And there's a t term, but I'm going to ignore that for a second. So this is how I'm assuming that my phi behaves in space, is e to the ikx minus kzz. When I drop that into here, the ikx gives me a minus k squared phi, and the kz gives me a plus kz squared phi, and that equals 0. Phi cancels out, so k equals kz. So I wrote kz over here, anticipating that I would need to do something about that, but we just erased the k. So the k on the x and the k on the z are the same because of Poisson's equation there. So now the last equation I need is to set the pressures equal to each other. So we'll take Navier-Stokes and we'll solve it for the pressure. So that we say that P equals what? Plus rho d phi dt minus 1/2 rho v squared plus rho g. Here, let's call phi is g times c. This is just mgh, like you did when you were a freshman. Plus gravitational times c1. Clean this up. So I got a rho. Let's carry out those rho. Let's take this rho all the way outside. And I get a minus d phi dt. I get a plus, because I factored out that thing, v squared plus g c1. Also equals rho prime times minus d phi prime dt plus 1/2 v prime squared plus g c prime. So these two things are equal. Plus some constant. I forgot about that constant. Where did that constant come from? I kind of lied to you a minute ago when I uncurled this equation. So I had this derivative that I undid. Realistically, you're left with a constant of integration. That should not have been 0. And I was being sloppy, and I apologize. So we have this constant of integration. So what is the constant of integration? We can sort that out. Okay, this is kind of a hairy equation. So we've got d phi dt, we've got a v, we've got a c1, phi v, c1. We've got this constant of integration. So we can sort out what the constant is by just looking at the background solution. And in the background solution, this is phi 1 and this is phi 1. These are all the perturbations. In the background solution, these go away, and so we're left with k is just equal to 1/2 rho u squared minus 1/2 rho u prime squared. Because the pressure has to be equal, to equal each other at C1 or at x equals 0, yeah.
Is that rho prime?
One of those is a prime. Yeah. Thanks. That one's a prime. So if we look at the background solution, then I just kill this term and this term and this term and this term, and all I'm left with is 1/2 v squared plus 1/2 v prime squared. And in the unperturbed state, those are just u. So I'm just left with this. So this constant of integration is just these. Now, okay, I had a constant from both terms. So I have one of these for the lower state and one of these for the upper state. I kind of combined those constants into one equation. The other thing we need to do is drop our Fourier analysis into here. And that's a little hairy, but it's not really all that bad. You just have to be careful. So one thing I would definitely encourage everyone while you're going through this problem is try to be very neat and organized while you're doing it. The more organized you are as you're writing stuff down, the better. This is hard, a do as I say, not as I do kind of thing. I'm not a particularly organized individual. So we drop our Fourier analysis into our pressure relation, and we're left with rho times this one becomes minus I times minus omega. Let's do it out the long way. So I got rho times this one becomes minus I omega, and I get a minus sign from the thing out front. Another thing I forgot to do, sorry. So this term v squared so this is v naught plus v1 squared, right? Where v naught is our background solution and v1 is our mean solution. If we expand in v naught and v1 the way we've been dealing with it, this is equal to u, the background velocity, minus d phi dx squared. Now if I expand this out, this is a headache because it's got stuff in squares. It's got the thing that I'm looking for. D phi 1 dx is the thing that I'm trying to solve for. And it's squared now. So what do? We get rid of the squared part. So we just expand this out, and you get u minus 2u d phi dx minus d phi plus d phi dx squared, and that, sorry, d phi dx squared, and that is a second order term, so we throw it out. So the velocity that I'm going to use in this equation goes from v squared to u minus 2u d by dx. Yeah.
Is that u squared?
This one's yeah, thanks. So this term I'm gonna replace by this, and this I'm gonna kill with the k. So, all right, I'm going to use my pressure term, constant of integration. I'm going to linearize this velocity and then do a little bit of algebra. And I'm left with rho times minus d phi 1 dt minus u. I'm running out of space. I need more board. Now there's more board. So u rho times minus d phi 1 dt minus u d phi 1 dx plus g c equals rho prime minus d phi 1 prime dt minus u prime d phi 1 prime dx g c. And now we plug in our Fourier modes, and we do this really carefully, and we're left with rho times minus I minus omega plus k u times c plus g times a equals rho prime times minus I minus omega prime. No, there's no omega prime. Minus omega plus k u prime c prime plus g a. So now I've just plugged in, this is my omega. I get a ku from this. I get a ga from this. Does everybody see how I went from here to here? Or does anybody have any questions about that? And then the rest is algebra. And let's see, is it obvious? So we've got this equation and this equation. And this equation and this equation. The easiest thing to do is just solve for one variable and stick it in here from there. So you solve for, so you'll see that k times c turns into omega k times a. So here I'm going to get something that gives me omega squareds and c squared, omega squareds and k squareds. Does that make sense? So then from there it's just a little bit of algebra to get to the dispersion relation. Do I see everything here? Yeah, I think so. And then the dispersion relationship we're left with is just omega over k equals rho u plus rho prime u prime over rho prime plus rho prime. Rho plus or minus square root of g over k rho minus rho prime over rho plus rho prime minus rho prime u minus u prime squared over rho plus rho prime squared big square root. Okay. Wow, there's a lot of hairy things in this. This is kind of an ugly dispersion relation, but the cool thing is that you can see instabilities and you can see waves in a couple of different scenarios. So we went through and we threw various things to zero, and we set up different boundary conditions. And the fact that some of these things under the square root blow up give us interesting physics. Okay, so that comprises the bulk of the hard homework problem. So the hard homework problem is just do this again, but then you'll have an extra term that goes like k d squared c dt squared, and that's the surface tension. And so from there you can see when we can suppress various quantities. Okay, that's all I gotta say for today. So homework due Thursday. Office hours tonight at 4, tomorrow at 4, Holler if that doesn't work for you. Homework on Friday. No, Thursday. Homework's due tomorrow.
Yeah.
I want to see it Thursday. So homework due tomorrow at the end of the day. Then we'll have the midterm next week.
Midterms on Tuesday.
Yeah.